Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Konrad.
Welcome, or hopefully welcome back to the Reliability Matters podcast. For those of you who continue to count, this is episode number 135. In today's increasingly connected and digital world, PCBs are the unsung heroes that power our devices, from smartphones to spacecraft. Yet, the art and science of designing these crucial components often go unnoticed. That's where this episode comes in. In this episode, I hope to unravel the mysteries of PCB design, tackle complex challenges, and unlock the secrets to creating high-performance, efficient, and reliable boards. Whether you're a seasoned PCB designer looking to sharpen your skills, a budding engineer eager to learn the ropes, or simply a tech enthusiast curious about the technology that shapes our lives, this episode has something for everyone. Today I'll be joined by Dr. Zach Peterson. Zach is a well-known researcher and electronics designer. In 2017, he founded Northwest Engineering Solutions as a technology consultancy and has since grown the company into an innovative design and manufacturing house for advanced electronic products. Zach conducted his applied physics PhD research in ZNO random laser theory and stability, and his Master's of Science physics research in chemisorbitive sensors for environmental monitoring at Portland State University. He also received his MBA in leadership and finance from Adams State University. Zach's work has been published in over a dozen peer-reviewed journals and conference proceedings, and he has written over, get this, 2,500 technical articles on PCB design for a number of companies. He is a member of IEEE Photonics Society, IEEE Electronics Packaging Society, the American Physical Society, and the Printed Circuit Engineering Association, or PCEA. He previously served as a voting member on the INCITS, I'm sure that stands for something, Quantum Computing Technical Advisory Committee, working on technical standards for quantum electronics, and he currently serves on the IEEE P31-86 working group focused on port interference, representing photonic signals using SPICE-class circuit simulators. Whew, that's a lot. Quite an underachiever, that Zach. And if Zach looks familiar to you, you may recognize him from the Altium OnTrack and Altium Academy video series and podcasts. After all that, it is my pleasure to welcome Dr. Zach Peterson to the program. Welcome, Zach, to the program. Thanks for being my guest today.
Yeah, happy to be here. I've seen a lot of episodes, and I'm subscribed on YouTube, and it's always been one of those ones where I've thought I'd like to talk to Mike. Now I get to do it.
Cool. Well, we're members of the Mutual Admiration Societies. I appreciate the work you do as well. I've heard of you before. Obviously, when we decided that we're going to get together and talk about this mysterious subject of board design, mysterious from my standpoint, I did even more research, and I'll tell you, we could have an entire episode just on your bio. Quite accomplished there. And I know we did before we went on air, we did a little talking, and you said, don't call me doctor. I'd already recorded that. And yeah, sometimes when I speak and they read my bio, which is a little bit shorter than yours, it's almost like hearing the sound of your own voice. It's like, I've heard that before. Let's get on with why I'm here rather than who I am, because what I have to say, I think, is more important than who is actually saying it. But I'm sure you go through that same experience, maybe amplified a little bit.
I've always just added the new interesting thing into the bio as it comes up, and then you don't think about how long it's getting and how long someone has to stand there and actually read all this stuff before a conference presentation or something.
Yeah, exactly.
You almost feel bad for the person who's introducing you.
Right. Yeah, they were told probably 10 seconds before, hey, can you introduce Zach or Mike or whoever? And they go, well, yeah, sure. And then they pick up this mini novel, right? And they're like, that's not what I signed up for. part of your bio was your work with quantum computing, and the acronym for the organization was INCITS. What does that stand for? Is it spoken, or is it just an acronym, or do we say however it's pronounced?
Yeah, I think it's an acronym, but it is a standards organization for a variety of different upcoming technologies. So we would just say insights.
Insights.
But it's
Okay.
it's
That
a
makes sense.
standards
Yeah.
organization that gathers people from academia and industry, brings them all together to hammer out standards for these upcoming technologies. So they have one, for example, AI. They have some for various aspects of cloud computing, some for photonics, things like this. Um, Standards groups, I think, are very important to participate in if you have the knowledge and expertise in that area. And a big reason for that is because it's kind of a way to give back, and ensure that the knowledge and experience you have is passed on to something useful and really informs the generation that comes after you. So I see it kind of as a volunteer work. And I know that there are people at companies who, they're paid to be part of standards groups. Like that's part of their job.
Right. Almost
But
like
when
a
you're
lobbyist. They're almost like lobbyists in the political world, but right? Because in some cases their motivation
that is
is
true. Yeah.
to have the standard benefit their company based on the products they sell, right? I mean, that's not a bad thing
That's
necessarily,
true.
but that may be the motivation behind it.
That is true, which is why these organizations will generally gather from across the
Yes.
industry, and so you
Right.
get competing voices in the room, and they all eventually figure out a way to come together and say, this is the way we're going to do things. So I think that's a good way to balance that, is to get multiple people in the room, and then you get
Sure.
people from academia who are kind of working on the next generation of stuff, and they have their input as well. So everybody can kind of flow together. So I guess if you look at it as lobbying, then those kinds of standard organizations are really the least bad way to do things.
Yeah. Yeah, I agree. I've had the experience of being on a standards committee, and it's a little. I'm not sure if I would prefer to grind glass in my eye or go to another standards committee meeting. But meaning they're painful. It's a birthing process, and it's every country heard from, but it is a good way to do it because it weeds out, the highs and the lows to a certain degree. Because so many people get to vote, and not just that, but once the technical committee creates a draft, then it has to go out for a vote, sometimes to an even larger committee. And that's where things get a little weird too. I know, I'm in the world of cleaning, and I remember after we produced a standard, it was actually a guide or a handbook rather. And I can read through that entire handbook, and I can almost tell you accurately who wrote or who contributed each section, because I can hear their voices. I know the way they speak. I know what's important to them. I know what products they sell or what services they provide. And I can hear that echoing in the words, right? It's because industry writes standards for industry. And so we can recognize the names in the industry. So how did you fall into this world of design?
Yeah, so you had mentioned earlier in my bio that I worked on random lasers. It's this very niche, esoteric topic in applied physics, or in nanoparticle physics, really. There's probably like, I don't know, 100 people on planet Earth that study this thing. But basically, they're very small clumps of randomly arranged particles that are basically a laser. You throw light or electricity at them, and they exhibit laser light. And the laser light that they emit forms these modes randomly because it's a totally randomly formed structure. But they're very interesting. They're very rich mathematically and very rich physically. And so that was where I had to learn really deeply everything about Maxwell's equations and then the application into quantum mechanics. And so that was the theoretical background that I got for doing stuff with Maxwell's equations, and then doing a lot of practical stuff with experimentation and measurement. And so all of that really forms the foundation that you need to know for RF design. So RF design came very naturally to me. I think for a lot of designers, they call it black magic because they don't they don't come from that world where they have to learn all of that stuff. So I did, and that's why I think I took so quickly to RF design, and that's really how I jumped into PCB design. I had done just little boards before in my graduate studies for experiments I needed to do. They were not professional at all. These were not products. This was just, I had to put some components in one place, so we'll do it on perf board. But actually getting into design, for like commercial products, my way in was through RF. And then the other stuff with high-speed digital really came naturally to me as well, because when you get into the very high speeds, some of those issues that you have with RF also start to appear in high-speed digital. And that's more and more the case as you get to these really high speeds like 112G, 224G. And then when you start learning why packaging is designed the way it is, you really see where the RF stuff starts to arise as a major bandwidth limiting factor.
Yeah, when I was doing a little research for our conversation, your work with the random laser, blah, 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 I literally copied and pasted that into Google, and I'm like, I don't understand what that is. And I felt like I was standing at the edge of a very deep precipice, this giant rabbit hole, and I'm like, do I want to go down there? I don't think I'm going to go down there. And I looked at about 8 or 9 papers written by other people, and all. One of them specifically on that subject, and some that use similar words. I'm not sure if they were really related, but anyway, wow, that's a deep hole. That's interesting stuff. And I'm like, okay, my brain is full today. I don't think I can take any more in because something's got to go if I'm going to bring something else in. So, one of the reasons I wanted to talk to you, Zach, about board design is, I'm on the assembly side of the business. We don't make boards. And to a certain degree, we don't design boards. Well, we generally don't design boards specifically. And much of my audience is also in the assembly business. Some are on the design side like you. But, I think, I've said this on the show before, I think most of our industry believes that circuit boards are delivered by storks, and they're dropped in parachutes like, babies. And they just come down onto our loading docks, ready to stick in the printer. And I don't think there's a really good understanding to how physically boards are fabricated. I know that's a whole process. But even more importantly, how they're designed. I know that our industry is well aware when something is designed that makes our life difficult. There's a big heavy connector way off the edge of the board, and the board is flexing. That's one crude example. In my world, there's a bottom terminated component that where cleaning is required, but they only gave us about a mil standoff to do it. And when you look at the surface tension of water, it's like, okay, the math isn't working here. We need to do something else. Who thought of that? Who thought that would be a good idea to put all the components on the bottom so you can't see them? Someone from the X-ray business probably thought of that because now they get to sell X-ray machines. So, but the point I'm making is those are just two very basic things that we deal with on the assembly side, and we shake our heads and go, how did this get out of the design door? So I don't think I just think there's this generation gap almost between designers, fabricators, and assemblers. And if we were all in the same room, if we all met at a bar, had a beer, and had our laptops out and designed something, it would probably be a whole different experience than these things being done in silos. And I think our side of the industry doesn't understand there are certain design rules, there are certain physics, there's certain things that physics, it's not going to change just because we don't find it easy to put together. You have all these design criteria you have to build to, and all these laws that you have to abide by that could make it a little difficult or challenging to assemble. So I want to kind of bring all this into the same room because you've got obviously design experience. You're probably very well aware of how boards are fabricated, and probably quite a bit, but at least something about the assembly industry. So let's try and kind of put it all in one room break it down. So the first question I have for you is, let's start with the basics. Can you explain the importance of adhering to design best practices in PCB design, and maybe define what some of those, we can't do everything because this is not a mini series, but what are some of those best practice designs that you embrace?
Yeah, that's a really great question because, best practice could mean a few different things depending on what's important in that particular board. It's interesting that you bring this up because I got asked to do an article for iConnect just recently, and I coined the term the Ferrari problem, and it relates to what we would consider to be PCB design best practices. And I have to thank Greg Papandrew for a discussion that he and I had where he kind of inspired me to come up with this term. But the Ferrari problem basically says that, those of us who do design education and who communicate design practices and best practices and things like this, we often give people the best of the best design practices, and then they feel the need to implement all of them. And then basically what they're doing is they're designing a Ferrari when really they need a Toyota or they need a Ford Pinto. They'll both get you to your destination. Do you really need the, awesome Rogers 3003 board with 24 layers and all this, super fine pitch BGAs and on and on and on down the list? I think that's a bit of an extreme example, but it really illustrates how complex you can make a board if you really want to and still adhere to all the best practices. So I always say that really you need a spec first before you start focusing on the best practices. You need to know what you need to design to and what the performance requirements are. And that's usually going to narrow you down to one or two best practices from a design side that really matter. Then there are other best practices in terms of DFM, DFA that you have to follow. And I'd say maybe,
and just for my audience sake,
what's
the acronym DFN, DFA? Design for?
DFM.
Yeah, M. DFM, I thought you said N. I'm sorry. Yeah. What's the A?
The A, design for assembly.
Okay, so manufacturing and assembly. Okay,
yeah, gotcha. Exactly. Manufacturing could really be the fabrication part, so maybe they should call it DFF, but you get the idea.
Right. Yeah. Yeah. No, it's interesting. When I think of DFM, I always think it only applies to assembly. I'm greedy. I want it all to apply to my industry, but obviously, fabrication is also manufacturing. They're manufacturing a board, so yeah, that makes sense.
Yeah. So the DFM requirements really come down to what can they fabricate, and you might be surprised, you might not be surprised, but oftentimes people will design something that is either really expensive to fabricate or it just can't be fabricated with their desired vendor. There could be several different reasons for that. They selected odd materials, like simple stuff like that. They selected odd materials that they don't stock, so now they've got to start shopping around. They decided to use feature sizes that are too small, whether it's drilled holes, whether it's trace sizes, things like this. They just use stuff that was too small, can't be fabricated. Or it can, but it's going to cost you got to add a zero onto your, fabrication price. Nobody likes to hear that.
Yeah, right.
Yeah. A lot of those problems, maybe 50% of them, can be solved just by leveraging your design tools. Because the design tools over the past, I don't know, maybe 10 or 15 years, let's say, have become a lot more aware of those DFM, DFA kind of issues. And so you can set up a lot of different constraints in the design tool. Doesn't matter if you're using Altium or Cadence or whatever else. They all have different ways to set up the design rules, but at the end of the day, you can get the design rules from your fabrication house into the design tool. And that's really going to help you avoid some of those, I guess you could say, simpler, what should be more obvious mistakes that are going to create a board that gets, no bid, or that requires a lot of changes in order to then get released into production. So yeah, the DFM, DFA stuff is something that a lot more designers have had to confront. And part of the reason for that is because, the CAD tools really let you do anything. You can put a 0.1 mil trace on a board if you want.
Sure.
Yeah.
The CAD system has no idea you can't build it. Right. Exactly.
Yeah, exactly.
But it's a theoretical thing.
Yeah. So, you have to do some setup on the front end, and that's where it comes back to having a spec and knowing where you're going to go. And so one of the things that we encourage people to do early on is to contact whoever they're going to be manufacturing with to get all of that information. Unfortunately, and I'm guilty of this, and a lot of other people are guilty of it as well, but most of the time we only think about contacting the fabricator. How often do we contact the assembler? I think we just kind of take it for granted that the assembler is just going to be able to wave their soldering iron, and everything's going to get onto the board with no problems.
Right. Yeah, exactly. And I interviewed a guy named Chris Denny, who is a COO for a small contract manufacturer and called Worthington Assembly. And he was telling a story that he had a customer who wanted a project built, and they gave him all the Gerbers and everything, and they said, you go ahead and get the boards fabricated. Okay, fine. And customer spec'd in a black solder mask, and for whatever reason. So, long story short, they were having tremendous bridging on this particular component. They just couldn't solder. I think it was a hand soldered, maybe a connector or something, but they were just having this bridging problem. And it after much rework, I think they didn't factor in rework on every part when they quoted it. They called the customer and they said, "We don't know what's going on. We think it might be related to this black solder mask. Can we just use a standard solder mask?" And the customer goes, "Yeah, I don't care." He goes, "Well, why did you want it black?" He goes, "I thought it looked cool." So they had more boards made and everything was perfect. So be careful what you ask for, right? I guess that was one of those specifications that didn't quite meet a DFA category.
Some of that stuff though, you don't even know until the boards get to assembly. Like, how am I supposed to know that I should be asking about how the solder mask color is going to affect bridging?
Right.
Like,
well, the problem is the wrong people know.
I would have had no idea.
Yeah, one of the criticisms, we go strange places in the show, but one of the criticisms of the whole 9/11 Commission, that whole tragic event, was that our various agencies within our government knew important bits of information, but they weren't all sharing. And I think in this case, maybe the board fab shop might realize, well, every time we do a black mask, we get so many of them back, right? It's not a good customer satisfaction thing. They may not understand why, but they're not talking to the assembler and they're not talking to the design people. They're just siloed. So everyone's got a little piece of information. As a podcast host, I have a piece of information about black solder mask, but that's not going to affect you if you're designing one. So the point is, we all have a stake in it, yet we don't all have an influence over it. So our stake is in someone else's influence. It's very siloed.
Well, and a lot of times, you're not fabricating and assembling in the same place.
Exactly.
I'm ordering the boards, or maybe using a contract manufacturer, and they might, talk directly to the fab vendor, so they know what's going on. But maybe I'm managing it myself, right?
Yeah.
And this is what we do. We'll manage that for you. We'll go to the fab house that's going to do what you need to do. They're going to have all the certifications. Then we're going to take it to an assembly house, and the assembly house is going to have, they're going to do whatever inspection you need as part of the assembly run. And the assembler doesn't know the fabricator. I'm the middleman between all of it, or one of my people is the middleman between all of it. So yeah, they both have the information, but like, they may not be telling me anything,
Right. Exactly. Right. Exactly. What are the key considerations when selecting the right PCB materials for a specific application, and how do these choices impact the overall design?
Oh man, this is a great question because it relates to stack up, and I think I was talking with Eric Bogatin on the Altium podcast, and I had made a remark, and he had agreed with it, but the remark I made was that I think probably 75% or something of the simplest SI, EMI problems, just the most basic stuff that all those PCB design blogs out there talk about, those are solved by picking the right materials and building the right stack up. Simple as that. If you know how to build a stack up, you are going to solve a lot of the simple problems. Just totally avoid them. And so the materials end of it becomes really important, because then once you start doing stuff in high-speed design, you have to know something about the material, or you have to rely on your fabricator's experience to tell you what to design. I am an advocate of designers being able to take the lead and do a controlled dielectric design. That's sometimes what it's called, controlled dielectric or controlled stack up, which is where I choose the materials, I understand the material specifications, and then I go and I design a stack up based on the available materials. And of course, the material vendor has to then supply the information I need. So they need to tell me their thicknesses, their DK values available. And then I build the stack up. Then I can take that to whichever fabrication partners I want to use and make sure that they're going to be able to, number one, procure those materials. Then number two, that they'll be able to actually, put it through their process and produce something that's going to meet spec. So, yeah, I'm an advocate of that. I don't always like the contacting the board fab shop and then saying, I need to have 10 mil traces that are 50 ohm impedance. Give me a stack up, right? They'll do that. And maybe they have a standard, stack up, like this is what we give everybody for this, and that's just the one that they run through in, thousands or tens of thousands of units every month or year or however long. So that's another direction you can go. But as you get to the more advanced end of the design spectrum, you're really going to have to take the lead on selecting materials. And so more advanced could mean several different things, right? It could be an RF board that needs to operate at much higher and higher and higher frequencies. It could be a power system, has to run at high voltage, right? And you need to make sure that this thing is going to be reliable for a long period of time. So now the curing agent matters. It could be such high voltage that maybe you have to worry about, let's say, dielectric shielding, things like this. So there are different issues that come up for your particular design. And if you know the performance requirements ahead of time, you can make a much more informed decision. Another one that's really common is, thermal, right? Thermal cycling, especially. Thermal cycling, of course, if you cycle too high on temperature, you go above the glass transition temperature. So you would want to make sure that you select a material that has the right glass transition temperature. Sometimes none of that matters, right? You can just pick the regular off-the-shelf FR4, if it's going to be just kind of a, maybe it's a throwaway consumer product, or, maybe it's an alarm clock, it's something really simple, right? Like, you don't need to go really deep on materials. You just need to go deep on making sure you can manufacture it at the scale that you need. And so that's working with the fab vendor and saying, okay, what's the standard stack up you're going to give me? What are my limitations on what I can do in the design? What can I do to maybe bring the cost down? Simple questions like that.
Yeah. I was hired as an expert witness in a civil litigation matter between an OEM and their contract manufacturer. And thank God for not choosing appropriate board materials, because it made me a lot of money for that gig. Long story, super short. They had a CAF problem, conductive phototic filament problem. And the reason they had the CAF problem wasn't so much the choice of board materials, but it was the lack of proper assembly. They didn't do any bake out. They potted their boards. They just had all sorts of issues. And they didn't clean well. And then they hand soldered something onto the board. They didn't clean it at all after that. And then, of course, no bake out. And it was a ECM, recipe book, right? And when we did all the discovery and we subpoenaed all their documents, and I'm looking through their statement of work to the contract manufacturer who was asked to procure the boards under board material, and this is an exact quote: "Nothing special. No, down and dirty FR4, nothing special." That was actually printed in their statement of work. Down and dirty FR4, nothing special. Now, we use that statement to kind of prove to the judge their frame of mind. Like, did they care about quality? When you use the foundation of your product, which is the circuit board, right? That's the foundation. That's supposedly the bedrock. And you say, yeah, down and dirty, nothing special. That led to it. And the point is, had they known that they were going to skip a bunch of steps, they probably should have spec'd in a board material that was a little bit more calf resistant. There are calf resistant, not calf proof, but more calf resistant materials they could choose. They never heard of the term calf, which I don't blame them. Most people have never heard of it until it bites them. And sometimes it's biting them and they don't even know it's biting them. They just think it's something else. But, that was a really good example of how, they had a choice between either assembling them right or getting a more robust material. So that's a little bit more forgiving. And I'm grateful that they chose the wrong. I'm grateful for down and dirty, nothing special, because, it sent me business, but that's from a selfish standpoint.
Well, if you're a fabricator, you're probably happy with down and dirty too, because you can make a little more margin on it.
Yeah, sure, absolutely. You don't have to order special materials and all of that. Describe for me the significance of component placement in PCB design. What strategies do you employ to optimize component placement for better performance and manufacturability or assembly?
Yeah, this is a great question. So in terms of how a designer approaches this, there are several things that can drive component placement into specific locations. Usually there's going to be something that's like hard requirement. We're not moving on this. A great example, the classic example is connectors, right? Connectors are probably the most common component where it must be at a specific location. We're not deviating on this. Antennas can also be like that. A lot of other times you will have a lot of freedom to pick where you want to put things such that you're really focusing on noise, EMI, and whether or not the board is going to just be routable or solvable, as Mike Creedon says it. So the noise issue is important, of course, when you're going to go into high volume, because you got to comply with EMC regulations. And so if you're approaching that on the front end as a major design requirement, then you can overcome, as I mentioned earlier, a lot of those simpler issues that cause EMC failures and that cause SI problems just by, number one, building the right stack up, but then number two is laying out different circuits that are going to be noise prone properly. So as if you're an engineer, you're a circuit designer, you probably have some insight into which circuits are going to produce a lot of noise, either as conducted noise seen on signals or radiated noise from some part of the board. So that's where you focus on placement and layout and really getting stuff close together so that you have everything you need in one location. It's easier to route. Also, it's going to have lower noise. That's really the first point. The other thing that really drives placement, I would say solvability, right? Is it going to be relatively easy to route such that I need the fewest number of layers possible? Now, I'm not one of these people that says that everything should be 2 layers. In fact, one thing I noticed from a lot of beginners is they have this idea that 4-layer boards are bad. Like they think they're going to, blow out their costs by going to 4 layers. They cost more, but this idea that like you'll never be able to afford a 4-layer board is kind of silly. And a lot of times, because of the ability to put ground in a 4-layer board and put it close to your circuits, you overcome those issues with EMI, EMC, and that's really going to be the magic bullet that helps you get past EMC testing and get your board into scale. So sometimes it's necessary. And the willingness to do those kinds of simple design decisions, sometimes are necessary. But it's funny because, I don't know if you've seen the 1-minute design review series that we've done for Altium.
No,
but basically people, yeah. So it's all short form, right? It's all on YouTube Shorts, but people will send us their boards and it's like, hey, roast my board on the channel, So we'll do a 1-minute design review and make it really, quick, concise, to the point. This is what you need to do. This is what's good. This is what's bad. And I get a lot of 2-layer board submissions. And you can tell who's new at board design just by looking at how they do a 2-layer board.
Interesting. Yeah, I'll have to look that up. That sounds like a fun show to watch. Roast my board. I like that. That's pretty good.
Yeah, exactly.
I hear a lot about, again, I'm not a board designer, but I hear a common phrase whenever I do watch this stuff or read papers on this subject, and that's signal integrity. So describe to me what signal integrity means, and how do you ensure signal integrity in high-speed PCB designs, and what techniques and tools do you use to mitigate signal integrity issues or potential issues?
Yeah, this is a great question, and of course a field that I care a lot about. So signal integrity, just kind of at the basic 30,000-foot view, is I want to ensure that the 1 or the 0 that I transmit from one component appears as a 1 or a 0 at the component that receives that signal, right? Boards are sending data between each other all the time. Or I guess the components on the boards are sending data between each other all the time. And you want to make sure that the data can be read at each component. So you have to design the traces on the boards correctly such that that data can flow and not get corrupted. That's kind of the simplest idea. The corollary to that is that if a signal does get corrupted, or if the trace is not designed properly, either you lose the signal or the signal creates a bunch of noise. Okay, so this is again gets back to EMI, EMC. And there are, again, simple things that you can do that will solve most or prevent most signal integrity problems in a board for the slower interfaces, or for like the GPIOs, SPI interface on a lot of components. That's where most designers, when they first get started, that's where most designers are working. They're probably using a microcontroller. It's got a set of GPIOs on it. It's got probably an SPI I2C interface on it. And the GPIOs and the SPI are going to be the single-ended signals that are most susceptible to noise, just because with today's advanced components, they tend to have faster rise times. There are things you can do to slow down the rise time, such as series resistance, and you can do that because those traces don't have an impedance specification, like they don't have an impedance requirement, I should say. But that's going to be where people first have their brush up with signal integrity. And the most common thing that people will see with signal integrity is really two things. One is ringing on the signal output, which is not a reflection thing, which is probably a ground bounce thing. And then they may see also some kind of ringing due to reflection, which tends to have a longer time constant associated with it, or not time constant, but a longer period associated with it. Mm-hmm. Or they just see excess noise at a receiver, right? Just too much noise. So a number of different things that can happen. And then if they start, going around with a near field probe and they have a lot of signals moving around the board, then they might measure radiated noise. And you can see it with a spectrum analyzer. In fact, there are a lot of people I follow on LinkedIn that like to show, example measurements of like what would happen on a spectrum analyzer measurement if I made this mistake in my PCB. So that's really informative because it really shows you what that kind of looks like in terms of an actual measurement. Then once you get to higher and higher frequencies, the issues with signal integrity become more about fitting within a standard. Okay, so we have something called channel compliance when we get up to really high frequencies. And that's where we have a standardized interface like DDR, like USB, like PCIe. I can go on and, keep naming the alphabet soup of standardized interfaces. But when you're working at high-speed digital, a lot of what you do is ensuring that you have designed the board such that you can place traces that are going to guarantee that the various performance aspects that you measure about those signals are going to fit within some list of requirements for that particular interface. So that is really more on the advanced end of the spectrum of signal integrity. Now, RF systems have their own signal integrity requirements. They're slightly different just because we're only working at one frequency and we're not working with a digital signal that has its power spectrum spread across basically from 0 to infinite frequency. So we don't have a large bandwidth. We really have one frequency and maybe a small range of frequencies around it that we have to work with in RF systems. But the approach is, pretty much the same, honestly. It's just what we analyze to say good signal integrity versus bad signal integrity. Those are slightly different things that we analyze in an RF system versus a digital system. But at the end of the day, the goal is really the same, right? We want to make sure that the RF signal that I send from, let's say, my RF ASIC ends up getting to the receiver or being broadcast from an antenna with enough power and with the correct waveform such that the system is going to be able to operate correctly. So we don't lose the signal and we don't distort the signal along its propagation path.
So we've mastered signal integrity in the last 3 minutes. We're sending ones and getting ones, and we're sending zeros and receiving zeros. But the board's overheating. Let's talk about thermal management. And and what techniques do you use to prevent the overheating of a component or a section of the board, and to ensure proper heat dissipation? What are some of the tricks of your trade there?
Yeah, so most people are going to just like throw heat sinks and throw fans at the problem until the problem goes away. Right, that's the simplest.
More thermal paste, more thermal paste, more heat sinks,
exactly, bigger heat sink, right?
Yeah.
That
or
kind
a fan, a heat sink with a fan in it. Yeah, we've seen those before.
Yeah, or put the fan right on the component, right? And that's actually what a lot of processors will do is they'll have a heat sink and then the fan is like literally on top of the heat sink. So that'll happen in the larger processors. In terms of thermal management, there's stuff you can do in the board itself, and then there's stuff you can do on the enclosure. The board itself, the amount of copper in the board really does transport heat. Now, there are people who I'm sure and I'm not going to name names, but there are some people who have written that things like planes and copper pour are totally meaningless for thermal management, as if copper does not conduct heat. When I talked to Mike Jopi, who was on the IPC 2152 Standards Committee, that guy has compiled more data on thermal management than I have ever seen anybody do. The man is obsessed. And it's good that he's obsessed because he's able to show that actually copper is beneficial for big surprise, right? Yeah. Metals are beneficial for removing heat from a hot component and transporting it around the board. So, copper in your board is also a big factor. And when you have a high-speed board that may have a large processor that is running with a lot of IOs active at once, and it is consuming a lot of power, it's going to generate a lot of heat. That heat does get transported around the board by the copper. So you can move the heat around the board if you're creative. And there are even so much more advanced techniques like using copper coins inside of the board, where you basically fill a cavity with copper and you have a heat sink that's now embedded in the board. Then once you have that copper in the board, you can attach that copper to something else, like a larger heat sink, like the enclosure itself, and then dump the heat into the enclosure. One of the systems
actually embedding the heatsink within the layers of the board, in essence.
Yeah, exactly. So it's literally filling up the interior of the board in one specific region with copper.
Interesting idea.
Yeah. Now another thing, once the heat is being dissipated away from a component, what do you do with it? One of the systems that I'm working on now actually dumps it into the enclosure, right? And so how you get the heat into the enclosure really depends, right? Could be through mechanical elements that are on the board, right? So like the screws and everything that you use to attach to any rails or points on the enclosure, right? Those are all going to accept heat and aid heat transport. And one spec that you might have on this type of system where the enclosure is being used as the heat sink is a temperature requirement or a safe to touch kind of requirement on that board. Another way to do that is with a thermal interface material. So you can actually bond the board directly to an enclosure via a thermal interface material. And that's going to give you a really wide area path for heat to transport away from the board and into the enclosure. Now, your enclosure heats up, but if your enclosure is large enough and it has enough thermal mass, it's fine.
Right.
It'll
The
heat up.
enclosure becomes a heat sink to a certain degree itself.
Yeah.
One of the things I'm a Mac guy, right? I like Mac computers, and I do a lot of content creation, which Macs are really good for, right? Probably not the best business computer, but great for creative stuff. But one of the things I just bought a new M2 or M3 Apple Silicon computer, and I don't know if there's a fan running. I can't hear it. And, I'm sitting with you can't see it because I have it masked out, but I have this, really expensive microphone, that's got pretty good noise rejection, but it can hear a fan like my MacBook Pro. That fan, this can hear, I filter it out, but it could hear it. I'm looking at this Mac on my desk here, and I know the fan's probably running because I'm doing a lot of processing right now, and nothing. They've mastered probably on a board level, obviously, but also on an enclosure level. They've managed to vent out all that heat from these, pretty gnarly processors, and do so very efficiently, I'd say.
Yeah, fans are, of course, very important, and selection of the right fan is very important for making sure you can get that heat out. And the noise from the fan, which you brought up, very interesting too.
I'm sure there's an electrical noise from the fan too, right? I mean, you got to deal with all that.
Oh yeah, there is. I mean, you're driving it with a switching signal, right? You're driving it with a PW, pulse width modulation, in order to control the speed of the fan. Right. And so, yes, there is the electrical noise, but also the mechanical noise itself.
Sure.
And then the rate, the speed at which the fan turns also influences the noise that you hear because it's getting into the audible range.
Sure.
One thing that you might like to do with one of those fans is drive it outside of the audible range, and so you're pushing the frequency up to a higher and higher level.
Right. It's there, you just can't hear it.
Yeah, exactly. Well, you could probably hear the airflow too if it's flowing through the right channel, right?
True.
So the airflow flowing through the channel will also influence, the noise that you hear.
Yeah. Well, so many factors that you don't consider until you start considering them.
Apple probably has a dedicated team just
for sound. Yeah, just for heat dissipation, just for sound. Yeah, all that. Yeah, they do put a lot of detail into what other companies would view as fairly meaningless, but they, that's why they're Apple. In the world of assembly and probably board design as well, we have our levels of expected reliability, and we define those through IPC Class 1, Class 2, Class 3, Space Addendum, et cetera. From a design standpoint, what are the basic differences between designing something for Class 1 versus 2 and 3? Are they close together, or is it just a designer's dream when you can just get away with one? Do you just not have to do a lot of things? Is 3 really, from a design standpoint, is it much different than a 1?
Yeah, from a 3 standpoint, there are some kind of simple things that have to happen that influence yield and that influence reliability long term that you have to do. The most common one is annular rings, right? This is the most commonly the one that is most commonly cited is annular rings. And then in order to overcome the annular ring issue, there are some fabrication houses that will say, put teardrops everywhere if this is going to be Class 3, things like that. The design choices for Class 3 are really meant to ensure that if there is something that happens within fabrication tolerance, you don't compromise the reliability. I think that's a big part of it, and that's kind of how I've always interpreted it after reading like the 2221 and then the 6012 standards. Going back to annular rings, because that's such a commonly cited example that I think people guidance on, there's going to be a little bit of tolerance on where that drill hit occurs, right? And you want to make sure there's enough copper left over to ensure that you have a reliable connection, and that you don't have an issue with adhesion of that pad onto that board. So that's kind of the philosophy that's taken with class 3 products. Whereas with class 1, like, who cares? If I measure 0 ohm resistance on that connection with a multimeter, then okay, great, it's good. I don't care, right? Because class 1 is throwaway product.
Sure. How do you optimize your designs for ease of manufacturing and assembly? We talked about DFA, DFM. What are some of the either things you want to embrace or things you want to avoid? And let me set up an example. Have you ever had? I tend to ask compound questions, so I do. It's fair to give me a compound answer. Have you ever had a situation where you've had to call your client and go, "No, don't do it like that," or "Why do you want to do it like this?" And let me make your contract manufacturer's life easier. I can avoid a phone call that you're going to get from them if I do it like this. That kind of example.
Yeah, I have. Well, okay, so let me back up. Usually we're given the schematics and we're doing the layout, right? So we really have the opportunity to make those decisions. Now, that being said, sometimes somebody will say, well, we need these trace widths and we need these, via sizes for our vertical transitions. We need to have the board in this space. So, they make these decisions that sometimes just make the layout more difficult, but it could also balloon their cost.
Right.
And the reason the cost balloons is because it's more complex, or just because it requires a more advanced process. And so sometimes you see requirements like that, and it's like, well, this is the kind of thing I might see on an HDI board. Why are you telling us to do it like this? Now, as a service bureau, at the end of the day, they're writing the check. And so if they say, I don't care, just make it, then you have to say, okay, I warned you, but sure, we'll make it the way you want it. Right. So you do have to, be willing to let your ego, sit on the sidelines and do what people are paying you to do sometimes. But that being said, when you have control over it, simplification in terms of fabrication, the number one option is just larger feature sizes, right? Do you really need a 4 mil trace? If you do, then there are ways to do it, especially to hit controlled impedance requirements. Do you really need 8 mil vias, or can we lay this out with 14 mil vias? Because it's a 6 mil difference, right? But that's a decent cost multiplier right there.
Sure.
The number of layers, right? If we're going for low cost, we're going for simpler, right? Do we really need 8 layers, or can we maybe find a way to consolidate this down to 6 layers? Or can we get it down to 4 layers even? Simple things like that. On the assembly side, assembly is one of those areas where, like I said earlier, we don't talk to them enough. The number one time I would say that I need to talk to an assembler is with a BGA that I've identified as needing blind buried vias. And really the questions then become, half of it is fabrication, half of it is assembly, right? First, the fabrication is, what can you do? And then the assembly side is, hey, these guys are telling us to do this. If we do this, can you guarantee reliability?
Right.
Or can you guarantee that we're not going to have intermittent failures or cracking or whatever? So that's where we really have to engage with both ends of it. And that's especially true once you get to smaller and smaller pitches. Once you're down to, these extremely fine, 0.3 or whatever pitches, all bets are off. Now you got to really make sure that your assembler knows what they're doing. But that then goes back to the component decision. You have to go back to the client. Do you really need this 0.35 pitch BGA, or can we use the exact same component in a QFN? And usually when you look at it objectively, you can probably find a reason to just go back to the other component that is going to have higher yield. It's going to make the board less complex. It's going to reduce your cost in fabrication and assembly. And especially like, with like going to a BGA versus a QFN, there is one really actually, there's more than one now that I think about it. There's more than one really popular group of microcontrollers that do this. They have the fine pitch BGA option, but then they have the exact same component in, LQFP or QFN,
Sure.
right? And
one of those is going to packages
require
for the same function, basically.
Oh yeah, yeah. One of those is going to require at least 2 HDI buildup layers. The other is not.
Right.
So take your pick. Do you really need the HDI approach? If that's what you want to pay for, we'll make it for you. But you're probably going to drop a 0 off of your per board and fabrication and assembly cost if you just go with this alternative package. So
right.
I think it takes experience to really be able to identify when that's the case. But like I said, sometimes customers are just like, yeah, I know this is a 6-inch by 6-inch board, but I really want that really tiny, microcontroller on the board. And it's like, you don't need it, but okay, we'll make it for you.
Yeah. Yes. Give the customer good advice, but ultimately they're the customer. And sometimes they get what they ask for. What role, if any, does artificial intelligence, AI, play in board design? Has it infiltrated your field?
It is starting to. I will say this: the major CAD companies, the big 3, or if you consider Zuken to be a major CAD company, the big 4, they are all debuting or are working on some kind of AI tool for something in the board design space. Some of those companies have made their AI tools public and they're out promoting them. Others have kept them a little closer to the chest. They're willing to discuss it privately, but they're not, putting out press releases. Then you have a bunch of startups, right? And the startups are really trying to tackle the whole problem of like placement and layout. I mean, they're really going full bore, like we're just going to go all the way here. And they're not focusing on any of the other stuff that happens in PCB design, like constraint definition, like integration with manufacturing, cloud, data management, all this other stuff that happens at the enterprise level. They're really just focusing on like, can we make something that places and routes? And I think, the long-term strategy for them is to either sell that technology or license it to the big 3 or the big 4, mm-hmm. or eventually they are able to grow to the point where it's like, okay, now we can add all these other features that people at the enterprise level care about. But right now what they're doing is they're trying to develop these tools that will accept the big 4 file formats and then apply the AI to the place and route problem and then spit out a placed and route board. And then you take it back into your CAD tool. Then you do your cleanup, you do any kind of library management, and then you do your outputs. So I don't think it's ever going to be a case where it's just like I go onto a website and it's like, make me a power regulator board or whatever.
Right.
That requires a level of mind reading that Elon Musk is still trying to solve.
Yeah, well, on his way to Mars, he'll have plenty of time to work on it.
There you go.
It's quite a long journey. It looks like what I'm hearing is the early days of AI integrated into board design is a little bit like the early days of maps, digital maps. And, I remember before we had GPS systems in our phones, I would rent cars from Hertz, and they had their never lost system. They literally bolted to the transmission hump, on the car. And it wasn't the early days, it wasn't very good. It knew how to go from point A to point B. It would route it, but it wouldn't route it the way a normal driver would prefer to drive it. It didn't take into account traffic patterns. It didn't take into account closed roads because it wasn't really live updated. In some cases, it didn't know that the street it wanted you to go north on is a southbound only street, one way. But it did route it. And I could just I can just imagine the early algorithms, which just had a digital, they digitized the map and they basically said, what's the shortest distance based on the pathways that are available. And it was very simple, not very human friendly, but very simple and very almost analog in a digital way. It was very like binary. It was like here to there, period. And now, I use maps or either Apple Maps or Google Maps or Waze or whatever. I use those all the time. And it'll tell me, hey, I can save you 86 seconds if you exit the freeway in the next quarter mile. I'll save you 86 seconds and or whatever. And I found a shorter route and there's a cop around the corner and all this stuff now. So I would imagine that AI will get better and might be able to come close to reading your mind. When you say, design me a power regulator board, it might turn around and ask you 10 more questions, which would be smart, right? Like, where's it going? What class do I build it to? What voltage is going to run through it? And what size does the enclosure have to be? And do I build up or do I build out? Those things it'll probably start getting smarter at, and it'll start learning design rules and all the things you talk about signal integrity and impedance and thermal dissipation and all of that. It will probably start learning and remembering that. That's my guess. But it still will take design review because it's still going to drive you on the wrong way of a one-way street at some point.
Yeah, I think that's true. I think the thing to remember about AI at this point is that the big thing that you have to do as a designer, if you're going to be doing anything with automated place and route, is that you have to be in charge of the constraints and you have to have them down to a T. And if the constraints aren't well defined, then just like you said, it's going to direct you northbound on a southbound street. I think the other thing that needs to happen also with AI and really with some of the AI developers is, sometimes there is less of a focus on solvability, but that's because there are other constraints that are more important. So I'll give you an example, right? Like there's one AI tool out there that there was a demo, or it was a GIF, but there was a demo that the founder showed on LinkedIn, and he was basically saying, look, it produces 30% fewer ghost wire crossings, which is great, right? If the only thing that you care about is air wire crossings, then yeah, the AI can probably get you to the minimal number of air wire crossings. The problem is that there are sometimes constraints that force you to place things in such a way where you will have high number of air wire crossings. Sure. It's unavoidable, So a great example is like, I have to put these connectors here, and then I have to put this circuit here because that's where my power is coming in. Simple things like that. The AI may not be able to properly formulate placement rules for those types of systems. So I think what you'll really see is a better interface for controlling when the AI does the automation of some of the, I guess you could say the manual BS that people don't like to do, when and where it does that. And that's really going to be very helpful for designers who just don't want to have to sit there and place each and every single resistor for the next 30 hours,
Sure.
Now, the CAD tools over the past have gotten pretty good at automating some of that to an extent. There are alignment and placement and, some automation tools that really help you grid stuff out so you can be more efficient and you can fit within those constraints. But I'm interested to see, a really good UI for an AI-based design tool, because the UI is really going to be what drives the adoption.
Exactly. Exactly. It needs to know the entire scope of the project. It needs to know a lot of factors before it can even start auto routing or whatever it's going to do.
And some of that stuff you figure out on the fly.
Sure.
You have a spec that's a 30,000 foot view, but sometimes you don't know what you have to do until you've placed half the board, and then you realize, oh crap, I've got this problem. Now I've got to readjust.
Yeah. Well, I know in my experience using like ChatGPT or Google's Baird, strange name, I'll ask it a question and then it'll give me an answer based on my question, and I'm like, oh damn, that's not exactly what I wanted. And I don't have to like resubmit the question. I'll just say, factor this in instead of that. And it remembers the question. And so I could see that almost as part of the UI in board design, where you ask for something, it lays it out, and you go, oh, I forgot to tell it this. Except now change it to here. So you can get the general layout, and then you can start small in increments, putting bookends on the design and caveats on the design, and without having to resubmit everything. We're getting deep down the rabbit hole about something that's not quite there yet, or not quite ready for prime time yet, but I think it will be. Last question, Zach, because we're about out of time. How do you stay updated with all this stuff? I mean, I like to say our industry moves at the speed of electrons, right? So literally and figuratively, things change. From the time we started talking, something in your world has changed, right? And maybe you don't know it yet. How do you know? How do you learn that? How do you know it? How do you keep up to date?
Oh, yeah, that's a great question. I feel like I have to prioritize certain things because that's what other people care about most. And I mean, in some ways, my job, not just for clients, but really working, with Altium is to be an encyclopedia on stuff. So, I feel like I'm constantly taking in new stuff. And so I've got to really prioritize what is most important. So I subscribe to quite a few newsletters. I subscribe to some company newsletters that, whether it's around supply chain, just, industry news, design topics, things like that. Mil-Aero, because, a lot of the projects I work on are in the Mil-Aero space. There are some Mil-Aero newsletters to pay attention to because I want to know, what people are working on and
Sure.
what the newest design approaches are, things like that. It's also just good to know what new products are coming out, because that really informs, what approaches you can take. So there are some companies that I follow just for their product announcements because it's interesting, Then, PCB update is always nice for the business side of it. They always put a lot of business news in there as well as some tech news. So it's a really nice mix. So definitely check out PCB update. I feel like you were highlighted at one point, PCB update. That might have been the first time I had heard about Reliability Matters. And then some of the other magazines that are out there that are still, produced as hard copies. Signal Integrity Journal, Microwave Journal, Defense and Aerospace Magazine. What's another one? Oh, yeah. Interference Technology, which I said I'm an editorial board member for them now. And then PCD&F. So I really try and pay attention to all of those big publications for what's going on. You get to read what people are talking about. You also get a good overview of some of the newest trends in those particular areas. Defense and Aerospace Magazine and then Microwave Journal are really great for that. Microwave Journal is top notch. Love those guys. Signal Integrity Journal too.
Lots of reading.
Yeah. Well, I'm going to be honest. I don't have time to deeply read everything.
Lots of skimming.
Do my best. There's a fair amount of skimming, yes. Yeah. Or it's just taking mental note. Oh, okay, this is going on. I don't have time to dig into it. I'm going to go on to the next thing. But, every so often you come across a couple of important topics where it's like, this is really critical for what I have to do these days. I'm going to dive into that.
You know what I do? The purpose of me doing research is for the show, and so I can sound a little bit intelligent with my questions. So what I do is I'll find say if you wrote an article or if another guest wrote an article, I'll copy and paste the text of that article into Word, and then I will have it auto-dictate or it'll read it out loud for me as I'm doing other things. So I might be writing a paper or I might be editing a podcast, and as I'm doing that, I'm hearing the article. Now, obviously, I'm not able to comprehend every word because I'm multitasking at this point. But every once in a while, I'll hear something and I'm like, oh, stop. And I'll stop what I'm doing. I'll go back to that. I'll play it back again. And it turns out, I can't read and do other things at the same time, but I can hear and do other things at the same time. And enough of it gets in to catch my attention and then I can pay more attention to it. That's how I do it.
I'm going to have to start doing that.
Yeah, it's a little, it's a little bit of takes only a few seconds, but just copy everything, paste it into Word. I don't care about the format of it. I'm only listening. I'm not reading at that point. And I listen to it, and then you can control the speed at which it reads. You could read it, have it read at 2x or 3x or 4x or whatever, and then you can even choose the voice. You are listening to a robot. It's not a natural voice. It's not like this AI-produced voice, this auto-tuned or a deep fake voice. It definitely is a robotic voice. But once you get used to that, and that'll get better. But once you get used to that, to me, it's a great way to multitask research and doing some productive things. For those of my audience that find this topic interesting and want to learn more about board design or maybe get some tips, Zach, in the intro, I talked about your company. Give us the 30-second elevator pitch on your company, and then I'll tell my audience how they can get a hold of you if they so desire.
Sure. So Northwest Engineering Solutions is a design firm that handles, of course, advanced designs and guides clients through the manufacturing process. We've worked with Fortune 500s all the way down to startups, and we can really guide companies through that entire process to get a product produced and then ready to scale. We also handle technical content and marketing, that kind of thing for, of course, Altium as well as some other companies. And so we're actually writing about the stuff we do, and then we do the stuff that we write about.
Yeah, excellent. You also have a personal website. Was it Zach?
Yes, I do.
ZachariahPeterson.com or ZachPeterson.com?
ZachariahPeterson.com. I should probably buy ZachPeterson.com and just redirect it to the other one at this point.
Yeah. Yeah, I bought MikeKonrad.com, and I was surprised. I checked it over the years if it's available, and it was never available. And one day, I think I'm quite literally lying in bed, and I'm like, I wonder if it's available. Boom, there it was. Not even a premium. Yep. Not that my name would be a premium, but it's $19. Boom, got it. And that's obviously the best way to find me. It's MikeKonrad.com for you, ZachariahPeterson.com. And for my audience who's just getting overwhelmed with all these URLs and email addresses, if you'd like to get a hold of Zach, either through his company or his personal website, both I found to be quite valuable, so it's worth a look. I will have Zach's contact information in the show notes. So if you're listening to this on your favorite podcast app, as soon as you pull over safely or get off the treadmill or wherever you are, just go to your podcast app, look at the show notes, and you'll find Zach's contact information there. If you're watching this on YouTube, right down there somewhere, there's a little button that says Show More. Click the Show More button, and you will get Zach's information. Zach Peterson, thank you. This is so interesting to me because I'm a little bit out of my end of the pool. I'm in your end of the pool, and I'm swimming. I'm not swimming quite as easily as I would in my end of the pool, but it's so interesting to hear what goes on behind the scenes. There's so much work that happens and thought processes that happen before the storks drop the board onto our loading docks. So thanks for explaining that to me and my audience, and I appreciate your generous donation of your time. I really appreciate it.
Well, thank you very much. Anytime you want to do this kind of thing, just let me know. And of course, you are welcome on the Altium podcast as well anytime.
Awesome. Well, thanks, Zach. And to my audience, we'll see you again in a couple of weeks. Well, that's another episode. Thanks for listening to or watching the Reliability Matters podcast. Be sure to subscribe to the podcast on your favorite podcast app. Or if you're watching this on YouTube, be sure and click the like, subscribe, and bell icons to be notified when new episodes are released. We release new episodes on the second and fourth Tuesday of every month. A special thanks to Circuit Assembly Magazine's PCB Chat at pcbchat.com and Ascendo Reliability at reliability.fm for syndicating the show. Thanks again for being part of our podcast family. Stay safe, stay healthy, stay happy, and perhaps most importantly, keep doing it right. And I'll see you again in 2 weeks.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.